Hello, I'm Beamer, your instructor, and here's the video that I promised you, showing you how to use Python and its libraries to actually go in and solve some statics problems. So anyway, let's get started. Here, let's see. Alright, so here is a blackboard, and we want to go to Material to Help. You want to click on this video, and this video will explain to you how to actually go in and Hello, this is Beamer Bevel, and today I'm going to show you how. Alright, so let's get out of this. And then what you want to do is, after you do all these instructions here, go in and do this command, and essentially this is the same way you installed all of these. You just basically go in and put this command in to the PowerShell, and if you don't do that, the graphics won't work. Then what you want to do is go in and download these 4 files here, or folders. These are Python files, and here's just introducing you to complex numbers and arrays, and here working with vectors, and then these are 2 examples of the books where we apply it. Okay? Alright. Now, let's go in and let's run some stuff. If you look at here, you should have an idle type icon, and this is the IDE, Integrated Development Environment, for running Python programs. And if you don't have this, you can actually go into here and find it in here, and actually go in and then transfer it to the desktop or run it from there. Alright, so let's double click on this, and here's your Python shell or idle. Now there's several ways you can run programs. You can actually run them from here by just typing in numbers, just like a calculator. Like here I can go 3 times 4 and 12, and I can do my whole program like this. But the problem with this, even though you can save the workspace and come back to it, it's just not organized really good, and it's not really good for programming. The way you really should do it is actually work with an external file, and with the external file, what you can do is you can actually go in and make changes as needed, really easy, and just run it. Okay, so what you do is you go to File, New File, and in here you put all the code that you normally would be putting here, you put in here, and then once you've done, you just basically go to Run, and you run it, and basically it shows the results over here. Now, I've already got some files here, so let's go in and open up one here. So here, and so let's open up complex numbers. Okay, and so here's a file that I actually typed everything in. Now notice every place that you have this pound sign, that's just a comment, okay, and that's just to help you see what's going on. And in this simple program here, well, it's not real simple, but in this program I'm using 2 libraries, the math library and the C math library. Here, the like trig functions, cosine, tangent, things like that, for real arguments are in this math library. If you're doing complex cosines and things like that, I'm not sure, I don't think you guys have done that in your courses, but if you take any advanced courses in complex variables, you will see it. So here you can do the cosine of a complex variable. Okay. Now the way you put numbers in is a little differently than you do with some of the other like C-based languages. Here with C, you'd have to go in and say, well, this is a float, and you have to specify the type and everything. But here you just go in and put your variable name and what you want to go in. And here we're putting exponential variable, so that's a good way to do it if you're just doing constant like that, so you can't be any simpler than that. And here everything, all the trig functions and stuff work with radians as it should be. Degrees are really useless unless you're a surveyor. but radians is just, from the very definition of what a radian is, makes it very, very useful measure of angle. So here what I'm doing is, let's say that you're given 45 degrees and you want to change it to the radian. Well, here's your typical formula. You multiply it times pi over 180, and that gives you in radians. Notice here that the pi constant is inside the math library, and so this is how you invoke stuff that's in the math library, math.pi. Now, it's a simpler way to do it. There's a function within math called radians, and so you just put the degrees here, and this gives you the answer in radians. If you want to go the other way, then you would be math.degrees, and here I'm saying math.pi over 4, and giving your angle over here. Now, to input a complex number, you basically go in and you put the name of it, and you can use the complex xy, the real and imaginary value, or you can do it x plus y times 1j. Okay, you can input complex numbers in polar coordinates. So here you got your magnitude z, and you're multiplying that c math exponent. And notice we're using c math, not math, because this is a complex argument. So anytime you're using exponential functions or trigonometric functions, and basically you're taking an complex number as an argument instead of a real value, then you need to invoke it through the c math. Okay, and so you can do conversions between polar and rectangular. This is unformatted type printing, formatted printing, and I'm going through this quick. You can look through this on your own and play around with it. Here, normals can store it only in rectangular form. So here I'm printing out some stuff here. And here we're doing about real and imaginary functions. Here you get some values here, how you can multiply. Here you have complex numbers. You can multiply them too. Wow, that's pretty easy. Much faster than using the calculator, I think. And then here you're printing out the results. Here I'm going in showing that you cannot do arithmetic on polar stored numbers, so you can read through that. Division, here I'm dividing complex numbers. Here it's basically showing some stuff that won't work. Power function. All angles must be in radians, so here we're doing the cosine, sine, tangent functions, then the arc tangents or inverse functions. Here's something to be aware of if you've done stuff. Actually, I think Basic, Visual Basic, and all the other languages always have an arc tangent and arc tangent 2. With the arc tangent here, you're going to have, you're not going to really resolve between different quadrants. Quadrants 1 and 3 will give you the same result. Quadrant 2 and 4 will give you the same result. And you can see by looking at the sine, the cosine and sine in each one of those quadrants. But if you want something that's going to give you an angle that's like between 0 and 360, then basically what you can do is put your y value and your x value in, and then you have the arctan 2. And so this will give you the angle in the correct quadrant. Here you won't know if it's in 1 or 3 by looking at it, but if you design the program, you will know. So anyway, and then we have our power functions, common log, log 10, the natural log to the base e is just log. Let me just say one thing. In higher level math courses, basically what you'll see is anytime you see log and you have to guess between whether that's natural or common, go ahead and assume that it's a natural log. If you're in a basic course, a basic calculus course like in undergraduate, then you know, probably you'll see log for common, and then you see ln for natural. So don't get hung up on that. And like I say, log is far more important uses of the natural log than it is the common. In electronics, we use the log 10 a lot in communication theory, but for the most part, this is really the powerhouse of logs to the natural log. Okay, and so here you get some values here, and all I'm doing here is just solving a simple circuit problem. This was I was giving this originally to my electronics class, and here we're going in and solving for some different values, and here I'm comparing it to some simulations. So anyway, that's it. Now, once you've written all the stuff you want, and you should use lots of comments, so if you come back in a couple of months or maybe even a couple of days later, you know what you did. Okay, so once you got this, you usually save it. Oops, I don't want to do save as. Do file, save. And then what you do is you basically go and run it, and your results show here. So you got a whole bunch of values here. I'm talking about power and watts and all kinds of good old stuff. Right. Okay, so lots of stuff there. All right, now let's go back over to here. And so we're done with this program here, this complex numbers. And so remember, we use CMath for functions that take a complex number as an argument, and you use math for functions that take a real value as the argument. Okay, so let's close this. Let's go over here and let's open another file, and we go to Documents, and we go to the vectors here, and this time we're going to use vectors. Okay, so let's open this up, and here's just using vectors with NumPy. So in this case we're importing math, and I just did math as it is, and then NumPy is NumPy. Later on you'll see I import math as MH. So here are two ways to assign vectors. You can do like two vectors in one line. So vector 1 is this, vector 2 is that. Or you can do it separately. Vector 1 equals the array 1, 2, 3. Vector 2 equals 3, 2, 1. And you can find the length of the vector by using the norm function. And this norm function is actually in the linear algebra module, which is in NumPy. And so I'm normalizing it, or finding the norm. Well, not really normalizing, but I'm finding the norm or length of the vector here. Okay. And an alternative way is to actually use the dot product of this. And recall that dot product is just one form of a inner product. Okay. And if you've taken a course in linear algebra, then you'll learn about inner products, and you'll learn the specific inner product called the dot product that's used so often. So anyway, this is by far the easiest way to do it. And here what I'm doing is adding two vectors. Well, one way is simply this way. Another way is to use the add function. We can do the inner product, which in the case, if you look in the Python documentation, you look at inner and dot, you'll see that they pretty much do the same thing for just vectors. If you start messing with matrices in here, then you get some different results between these two. But if you're just working with vectors, you can either do np.inner or np.dot to actually do it. But keep in mind that dot is just one particular type of inner product, or one thing. Okay. Now here what we're doing is just multiplying two vectors, and this is a little weird here. This is not your normal type multiplication here. What it's actually doing is it's multiplying the x components together, the y components together, the z components, but it's keeping it as a vector. It's not like the dot product. And then here I'm just multiplying a scalar times a vector. Here I'm doing the outer product, and the outer product is defined as this. The ij component of this matrix is equal to the ith component of A times the j component of B. So don't worry about that. Cross products, if you get into tensors and do some stuff like that in higher level math, you'll see some things that look like this. So the cross product we will be using, and the dot product, inner product we'll be using in this course. Okay, so here we're just printing out the results. These are the components of the vector, and this is how you access the components of the vector. You just put brackets, and a 0 index is the x, and the y, and then the z. And here what I'm doing is I'm basically going in and I'm doing the direction cosines. Now remember, the direction cosines are defined as basically the length of the vector dividing into like the x component here. The y component would be a 1, the z would be a 2 here. And so this is the direction cosine. And here what I do is get that in radians. What I do is I basically, well, is what I'll be in. I basically go in and take this in here and do the arc cosine of that. And so I print this out, and then if I want it in degrees, I can just use the degrees function. And here I'm basically going in and doing the norm, the V1 norm 1 and V1 norm 2 that we did up here. Okay, and then here I'm doing the outer and cross. Here I'm doing something a little different. What I'm doing is creating an array of vectors. So I'm kind of like stacking them together. So I got vector equals np array, vector 0, 1, 2. So these are actually 3 vectors. It's an array of vectors, a vector of vectors then. And so I'm printing them out. And here what I'm doing is I'm actually going in and using a little for loop. And so here what I'm doing is saying for each vector in vect, and there's these 3 vectors are there, I print it, and then basically all I do is just basically W. I'm just going in and adding all 3 of these vectors together, and then I'm printing it out. Okay, so this is just a simple thing. So let's go ahead and let's run it. And so there's the results. Here's the 2 vectors. Here's the components, 1, 2, 3, 1, 2, 3. Cosine, radians, degrees. This is the length of vector 1. This is the length of vector 2. I'm adding 2 vectors. You can do it this way or this way. Taking the inner product, or dot product, and then v1 times v2, then 4 times vector, and then v out, then v cross, and then here's the vectors that I combined down to here, and then essentially all I'm doing here is just printing out all the results. Okay, good enough. Now let's go and let's, oh, I killed that one, but that's okay. Let's kill this, and let's go and bring back up idle again. And so let's go in and let's open one of the example problems. Okay, so here let's pull in 2.9. Okay, and so in this example here, it's a really simple one. You have f1 vector, f2 vector, and you have a resultant vector, and you're essentially given f1 and fr, and you're asked to find f2. And with the f1, you're actually given direction cosines and the magnitude, so you need to do some calculations there. But for this problem here, all we need is numpy and math h, and notice I'm doing as mh here. So we look at the drawing of the figure associated with this problem, and we see that the magnitude of f1 is 300, and we figure the angles, direction cosines, and I put a d here to signify that these are in degrees. And then for vector fr, the resultant, we're giving this 800, and it's along the y component, or y axis. Okay, the next thing we do is we go in and we want to convert these to radians, because we need the angles in radians if we're going to use the sines and cosines. So we do this function to do that. Then we can calculate the x component, the y, and the z component by basically using the direction cosines and the magnitude. And then what I do is I go and create f1, the vector, by just using the np.array. Now for the resultant, it's really simple. It's just the 800 magnitude, and it's along the y-axis. Now to solve for f2, really simple. Since fr equals f1 plus f2, then essentially f2 is just going to be fr minus f1. Okay, you can't get any easier than that. And so now I have f2, but I want to find the direction cosines, alpha and the beta and the gamma for that. And so you notice I have two lines here, one where I get the angle in radians, and then another where I get it in degrees. So I do that for all three. And to get the length of the vector, or the magnitude of f2, all I do is I just use this function we've been using all along. And then here all I'm doing is essentially going in and printing the results. Okay, so you can't be any simpler than that. And notice that if I had a different problem, I could go in and change these. I could change this. I could change this. But and I could easily go in and change the problem where I'm looking for fr instead of this. But writing a program for something that's going to be a common problem is a really good thing to do, because you can easily go in and change the inputs to whatever you want. Or if you're doing something and you want to say, what if I do this, or what if I do that? Well, that makes this really easy. It's like a real major pain in the butt to actually go in and do all this by hand. And somebody says, well, what if I change the angle here? What would you get? What if I change that? Well, hey, you want to do it this way. Now, a lot of people, especially civil engineering types, like to use Excel. Okay, and that's okay, but I hate Excel, and I really think this is much better than Excel. But hey, if you want to use Excel and you're a civil engineer, then you probably should use that. Otherwise, they'd probably laugh at you. But if you're a mechanical or electrical engineer, I really recommend doing something like this. So anyway, let's get out of this one and let's go to a more complicated problem. So let's go to File, and let's open up this one here, Documents, and here we're going to do 3.7. Okay, now this one here is essentially you have 4 cables. One cable is hanging down with a 40-pound crate, and then you have 3 supporting cables, AB, AC, and AD. And so we need to figure out what the forces are in these supporting cables. And that's based on the geometry that we can see in this figure. Now, let me just point out one thing. Here it says 40 pounds. So when you see that, and you see a 40-pound crate, then the first thing is going to go in your mind is says, okay, well, pounds, okay, then are we talking about pounds mass? Are we talking about pounds force? You know, if we're talking about pounds force, then essentially we could be either English engineering or British gravitational systems. If we say 40 pounds mass, then that pretty much says we're in English engineering. But the way the problem is stated is pretty obvious, or it's a safe bet to go in and say, well, we're talking about 40 pounds force, which is what weight is. Okay, when you see the word weight, you're talking about a force that's due to the gravitational acceleration or attraction. Okay, so anyway, we're using NumPy and math, and so the first thing I want to do is go in and establish the vectors, or unit vectors, that are associated with each one of the cables, and we're going to let the point A be the origin. We don't have to. We could use whatever we want to, and different problems you want to use something else here, but in this case it makes sense to use that. And then we go in and we find the position vectors of these points. This is at that point, at that position, this is that position. For D, the distance is not given, and it's not really needed, because all we need is just a vector pointing along the x-axis, and it's along the positive axis. And so I just put a 1 here. I could have put anything here, and I'm going to normalize it later, but put a 1 there, so the easiest thing to do. And the same thing for the direction of the weight is along the negative z-axis. And so they didn't really put coordinates there, but hey, it's just put a -1 there. And the magnitude of the weight is 40. Okay, so the next thing I need to do is I need to make unit vectors out of these vectors here. And what I'm doing here is I'm actually going in and finding the vectors from these points, and since all these are zeros, I really didn't have to do this step, but by doing this step I make the solution more general. And that's something you should look at when you're going in and writing a program for a particular problem, is if it's pretty easy or just a step or two to go in and generalize the problem where it's more appropriate for a general class of problems like this, then do it. And that's what I'm doing here. Okay, and so here I'm normalizing the vectors, and the way I do that is I basically just go in and take this vector and divide by the length, and so that will basically go in and normalize this to unit vectors. And so I'm doing each one of these here. And so just summarizing what we have is we're going to have, we know these unit vectors along the directions of the cables. What we don't know is the actual force along there, or the magnitude of the force there. We do know the weight is 40 pounds for the crate, but we don't know these. And so what we have is a system of linear equations, and we need to solve for FB, FC, and FD. So here's how we do that. The first thing we want to do is do a stack here. So we're doing NP vertical stack of the vectors, AB, AC, and AD. So these are the coefficients here of that. And then what I want to do is I want to basically do a transpose to get this in the right format for the matrix. And here I need to make this negative here so that I have a positive thing. You know, whenever you're doing a system of linear equations and you got your constant on the left side, then you move it to the right side and it becomes a different sign, essentially. And then I need the basically take the vector B as I want the transpose of this to make it a column vector. And then I just basically go and call this command here. This is the linear algebra solve, and so it solves a system of linear equations where A is your matrix and B is your constant vector. And so the results are basically going to be down here. The C's, this will be the X, Y, and Z are the FB, FC, and FD values. And yeah, so here I'm just printing the results. So let's go and look and see what we get. And there you go. We get along the AB cable, we got 23.5 pounds. FAC, we got 23.58. And that's not a big surprise because of symmetry. And then FAD, 15 pounds. So there you go. You know, with just a little bit of time here. Let me bring that back up. I didn't want to kill that. This is not really much of a program, and I mean, all we're doing is just writing down numbers. This is pretty much the same kind of thing we would have been doing by hand, but it's a little bit quicker and much less mistakes. Okay, and so here we could have changed things. We could have changed the points here. I mean, this is a really general program now. We can change all these values. We could change the weight and come up with a totally different problem. Or, you know, if we went in and did analysis here and we found out that the force in the cable or the tension in the cable was too much for the particular cable, we could have gone in and changed the points and played around with this to see, you know, what did we really need. Okay, so hopefully this will help you as far as going in and applying this to some other problems. And anyway, we can talk some more about this the next time we meet. So good luck, and let me just say goodbye. So goodbye, have fun. Hopefully you enjoyed this, and I think you're going to have a lot of fun with this. And so till next time, have fun.